Okay, welcome to Introduction to Photonics. We've been talking about the particle nature of light in the past few lectures. So we introduced what a photon is and what are the properties of photons. And then towards the end of last week, we had talked about interaction of light with matter. So we started talking about absorption of light. We looked at the specific example of light getting absorbed in rhodomin 6G, and that sort of absorption process essentially required us to tune into the photon picture and say that if the photon energy corresponds to the energy difference in this particular material, then it's likely to get absorbed. So we will continue to build on that picture. So what we will do for the next few weeks is to identify the fundamental principles of photon interaction with atoms. We just started doing that. We will go into that a little more detail, and the specific motivation for considering that is we want to understand light generation and amplification, okay? Because so far we have been looking at ray optics, wave optics, electromagnetic optics, photon optics. And in all of this, we just figured there is some source out there which is giving us all this light. Now, that source, how does that work, right? So, what goes into explaining light generation and amplification? And in certain ways, once we understand this, then we will be in a better position to understand why certain sources are not so temporally coherent, why other sources are temporally coherent, why certain sources are spatially coherent or not, all those things we'll be able to explain once we understand this. Okay, to understand this, let's just consider an atom once again, just like we did in one of the previous lectures. We have an atom with the energy levels, let us say E1 and E2, E2 being greater than E1, and let us see what all are possible between E1 and E2, okay. So, we already said one process that is possible is this light absorption, through which if you come in with h nu such that h nu corresponds to the energy difference between these two levels, that is h2 is equal to E2 minus E1, then you have an absorption process happening, right. Now, that energy cannot stay in E2 forever, because it's one of the higher orbitals. It is what you call as a metastable state, so it has to give up its energy, okay. It can potentially give up that energy by emitting a photon, okay, in what we call as a spontaneous manner, okay. So, it can emit a photon under certain conditions in a spontaneous manner. We want to actually figure out what are those conditions as we move on, but let us just assume that is one possibility. Or it could also have this case where while this atom is held at E2, a photon with energy h nu comes by and it stimulates this transition, okay. It encourages this atom to give up its energy, in which case it emits two photons. You come in with one photon, you go out with two photons with the same energy h nu, and such that the other photon that is emitted is absolutely a clone of the incoming photon. Okay. So, what do we mean by that in terms of light quantities? It has the same direction, it has the same phase, it has the same frequency as the incoming photon. Okay. So, it essentially generates a clone, and this is something that we can build up towards amplification of photons potentially as we move on. Okay. So, that is process number 3, which we will call as stimulated emission. Now, spontaneous emission is sort of a misnomer, because spontaneous means like the instant this atom goes to the higher energy level, it spontaneously emits that, right. And it turns out that is not the case, as you might have found out through the absorption experiments we did last week. It spends a finite time in that higher energy level before it gets emitted. As long as you understand that part is fine. But stimulated emission, on the other hand, is something that happens the moment that photon comes by. Immediately, if those other energy considerations are satisfied, it immediately emits photon. So, stimulated emission in some ways is more spontaneous than spontaneous emission, okay, if you can handle that. Well, yeah, the question is, why is the frequency the same? At this point, we are just considering 2 energy levels. Okay, we will go on to the picture where we consider a band of energy levels in the excited state and band of energy levels in the ground state and all. We will come to that. Okay, at this point, it's so. Of course, you may also argue that if you have a certain probability of emitting a photon between these 2 energy levels, the probability of absorbing the photon is the same, right. If what comes down can also go up and vice versa in this particular case. But let us just consider this case first, and then we can write what is called a rate equation. Okay, what is a rate equation? We are tracking the rate at which all these 3 processes happen. Okay. So, we will write under steady state conditions. What do I mean by steady state conditions? This is happening continuously. Okay, so the rates do not change. It's not like you just flipped a switch and you are immediately after that tracking this. You are letting things come to some sort of equality, and then you are observing this. That is what steady state conditions mean. If you are looking at immediately after you switch on something, what is that called? Transient conditions, right. So, we are not looking at the transient condition, we are looking at a steady state condition. So, under steady state condition, you can say that the rate at which the absorption process happens, assuming that the energy does not get lost in any other way, then the rate at which the absorption happens has to be equal to the rate of spontaneous emission plus stimulated emission, right. Spontaneous emission is this one, stimulated is this particular process, right. So, you absorb certain photons, right, and you go to the higher energy level. From that energy level, you either spontaneously emit, or if you have an incoming photon at that time, you can actually have stimulated emission also happening. Okay. Now, if you want to quantify this, as I mentioned earlier, these are all probabilistic events. So, there has got to be a probability density associated with all of these things. And so, we can basically say for this absorption process to happen, you need to have a certain number of atoms in the ground state, right, at energy level 1. If there are no atoms at energy level 1, then that absorption event cannot happen, right. So, let us just also track the number density of atoms in this level versus this level. Okay. So, we are saying that this has got to depend on number density of atoms in that lower energy level multiplied by some probability density, let us just call that P absorption, right, that is the probability density, and there may be some constant associated with this. Let us call that constant B prime. We will define what this constant means in a few minutes. Okay. And similarly, as far as spontaneous emission concerned, spontaneous emission happens at a particular rate. It certainly depends on N2, right. Only if the atom is in that excited state is going to have spontaneous emission, otherwise that you cannot have emission, right. So, it certainly depends on N2, and let us say that rate at which this emission happens is proportional, the proportionality constant we call that as A. And then when we consider stimulated emission, that also depends on the number of atoms that are in the excited state. It emits with a certain probability density that we can call as PM, right, and that also happens at a rate, let us say it is proportional to B. Okay. Now, so what is essentially different between the spontaneous and simulated process is that, you know, PEM, the probability density of emission, which actually depends on the probability that a photon comes by. Okay. So, that actually determines what that PM is. Okay. Now, in this sort of a system, simple system with two energy levels, you can say that the probability density of emission and the probability density of absorption is roughly equal, right. So, if we assume that if this is equal, then you can get an expression for this probability density of emission, and so that is just a matter of substituting, instead of PABS you substitute PEM and then rearranging terms, and when you do that what you get is A N2 divided by B prime N1 minus B N2, which you can rewrite. Let us say you divide the numerator and denominator by a factor of B and 2. So, you can write this as A over B divided by B prime over B multiplied by N1 over N2 minus 1. Okay. So, rho EM, we have some expression like this, and this is exactly what Einstein was doing 115 years ago. right. So, he wrote all these equations and then he came up with this, and he was looking at this. To his credit, he recognized that this looks very similar to what Planck had observed for a blackbody radiation. Okay. So, he said this is similar. So, in that case also Planck had derived an expression for this emission probability density, and so Einstein basically said, okay, this is similar to Planck's rho em PEM for blackbody radiation. Okay. So let us see what that actually gives us, right. So, I have this atomic system, and at this point it also helps to understand what blackbody radiation is all about. So, as you know, blackbody radiation is something that happens when you heat up a material to high temperatures, okay. And to explain what happens to the material at high temperatures, okay, let us just look at this picture, right. So, when you consider any material, it is going to have multiple energy levels. Let me just draw this. So, we talked about only 2 energy levels, but in general any arbitrary material may have multiple energy levels associated with this. Once again, these are all higher orbitals that are possible for a given atom. The question is, what is the probability that an electron may exist in one of the higher energy levels, okay, under the specific case of thermal excitation. Why thermal excitation? Because that is what blackbody radiation is about, right. So, it is essentially thermal excitation. And to explain that, we will have to essentially go to what Boltzmann came up with, where he said that under thermal equilibrium conditions. So, what does thermal equilibrium conditions mean? That you have elevated the atoms to a particular temperature, you subjected them to a particular temperature and you are holding them there, okay. So, things are not changing rapidly around that point, okay. Under thermal equilibrium conditions, the probability that you will find an electron at an energy level Em, let's basically say this corresponds to E1, E2, E3, E4, E5 and all that, right, and some arbitrary energy level Em. The probability that you will find an electron occupying an energy level Em, you are saying that that would be proportional to exponential of minus Em over kBt, where kB is what? It is the Boltzmann constant, right. So, and kBT now corresponds to some energy term, right. So, that is essentially your thermal energy. So, if you examine this closely, what it says is higher the thermal energy, more is the probability that an electron will occupy one of the higher energy levels. In other words, if T is 0, T is absolute 0, thermal energy is 0, all my electrons are going to be only in my valence orbital, right. They are not going to, you will not find any electron in any of the higher energy levels, right. So, but we are considering blackbody radiation where we are exciting this body or subjecting that body to high temperature, and in that case higher the temperature, higher will be the energy, the probability that you will find an electron at a higher energy level, right. And so we can draw that here. So, what it says is if I am plotting the probability of finding an electron at a energy level Em, where M could be anything from 1 to whatever, that probability will be an exponential, okay. So, you have probability being higher for lower energy levels than higher energy levels, okay. So, in this case, if we have, if there are n number of atoms, if there are n number of atoms, then what we can say is Nm, which corresponds to the number of atoms at energy level Em, Nm over n will correspond to the probability that you have an electron in that excited state Em, okay. And this implies that if you are looking at the relative numbers between two energy levels, why are we interested in that? Because here we have a factor N1 over N2, right. So, we want to see under thermal equilibrium conditions what will be N1 over N2. In this case, you can write it as N2 over N1 is going to be equal to exponential of minus E2 minus E1 divided by kBT. And let us look at that for a second. What it says is that if E2 minus E1, let us say it is 100 milli electron volt, right, if that is the energy difference. If I am at room temperature where kBT would correspond to about 25.6 milli electron volt, okay. If I am at room temperature, then N2 will be far less than N1. On the other hand, if I heat up that material, okay, to a elevated temperature, maybe 100 degrees centigrade, there you may actually have energy corresponding to 100 electron volt, in which case you have equal number of atoms in the high excited level compared to the ground level, okay. So, that is what this means. Now, and of course, I can write this simply as exponential of minus delta E over kBT, right. Now, I can plug this back into what Einstein had observed, right. I would then get the expression that the emission probability density is going to be equal to A over B divided by B prime over B exponential of delta E over kBT, but from the perspective of emission, what does delta E correspond to? The energy of the photon, right. So, the photon that is emitted will correspond to h nu. So, I can write this as h nu over kBT minus 1, okay. And Einstein just observed that this is once again very close to, very similar to what Planck had observed, provided A over B can be substituted by what Planck had derived as this factor 8 pi multiplied by the Planck's constant multiplied by mu cube over c cube, which you can choose to write as 1 over lambda cube, and B prime equal to B, right, or B prime by B equal to 1, which essentially means B prime is equal to B. So, if you substitute these constants A, B and B prime by these factors, this is exactly what Planck had observed, okay. So then he said, okay, then all these are consistent with Planck's observation. So, only thing that Einstein is adding here over what Planck was observing was Planck was observing only radiation as spontaneously emitted radiation, whereas now Einstein observed that there could be actually stimulated emission as well, okay. And further, if we, what he was observing was this A, this constant A is actually providing the probability density of spontaneous emission, and that is actually inversely proportional to the spontaneous lifetime, okay. And what is spontaneous lifetime? We discussed that last week. If you are tracking the number density in that excited state N2 as a function of t, the spontaneous emission is going to happen such a way that this comes down exponentially, okay. If you say this is normalized to 1, where it goes to 1 over E, that corresponding time is what we call as the spontaneous lifetime. So, once again, like I was mentioning last week, when people think about spontaneous lifetime, they think that, okay, this atom gets excited, goes to that higher energy level, and that specific electron which goes to the higher energy level spends this specific time and then it gets emitted. No, that is the wrong picture, right. It is not like it spends that much time and gets emitted, it gets emitted all along, right. That is what this means, it is getting emitted all along. If N2 is reducing as a function of time, that means the spontaneous emission is happening all along, It's just that where it goes to 1 over E, that's what we characterize as this spontaneous lifetime. Okay. So, it gives you some idea as to the time scale over which most of the emission happens, but it is not like a delay, a deterministic delay that some people may think of. Okay. And given this, you define B as or you just substitute, since A over B is already given by this expression, you substitute in that, and you can get an expression for B, which is lambda cube over 8 pi h TSP. Okay. We started with just a 2-level system. We tracked what all the possible events that can happen, absorption, spontaneous emission, stimulated emission. We were tracking the rates of all of this, and through that we were actually getting an expression for the probability density for the emission process. And like we said, Einstein said it's similar to what we have for the Planck's expression for blackbody radiation. And to give a background of that, we went back and looked at this thermal equilibrium conditions. What Boltzmann law says is that probability of occupying a higher energy level depends on the thermal energy, right. So, you have higher probability for more thermal energy, and so we got this expression for N1 over N2. We found N2 over N1, but you invert that, you get N1 over N2, which is what we plugged it back into the expression for the probability density of emission, and we said okay, it's all consistent with Planck's blackbody radiation theory. Okay, at this point I want to bring your attention to a collection of atoms. Okay, so there was a question about that earlier. So, in reality we are typically dealing with a collection of atoms. So, when we deal with a collection of atoms, what happens in the corresponding energy levels, or the probability that you will find an electron in a particular energy level, is actually different for two different classes of systems. One is, you can consider this as a dilute gas of atoms. Okay, it's just a dilute gas of atoms that are dispersed in this host medium, which of course holds good for gases, holds good for relatively low concentration solutions, that the kind of solutions that you are dealing with, rhodamin 6G in methanol or something like that. So that's that, or even in a solid, in a glass matrix, you are doping it with some, let's say some rare earth ion, okay. The typical doping densities that you are able to accomplish, you can pretty much consider that as dilute gas of atoms. Now, this is different from another system where you have periodic arrangement of atoms, okay, specifically with overlapping wave functions. Does that remind you of something? Periodic potential wells whose wave functions are overlapping each other. Does that remind you of something? That is what you find in semiconductors, right. So, in semiconductors you typically have this periodic arrangement of atoms with overlapping wave functions. What is the effect of that? Because of this, what do you have in semiconductors? Huh? A particular characteristic of semiconductors. Band gap, right? You have this concept of band gap coming to the picture based on this this periodicity with which the potential wells are located, and you have this overlapping wave functions. So, when you draw the what is called the EK diagram, energy versus momentum diagram, right, you find that you have something called a conduction band and a valence band, and you have certain energy levels between that which are forbidden, which you call as band gap energy. So, it turns out that when you look at the probability of an electron occupying one of these energy levels, right, one of these energy levels, this cannot be described by Boltzmann statistics. Here in the dilute gas of atoms, we said, okay, you have energy levels like this, right, and here we said, okay, we can describe the probability that you have an electron in one of the higher energy levels is exponentially distributed, right, and so this is P of EM, right. So it's lower probability as you go to higher energy levels, but here it's not the same. What you have here is another distribution which hinges around an energy, a characteristic energy called the Fermi energy, and if you are tracking f of E, let us say that is the energy, that is the probability that an electron is occupying one of these energy levels, that actually is a value from 0 to 1 and has a value of 0.5 at the Fermi energy, right. That is how you define the Fermi energy. And in this case, when we define that f of E, that actually follows what is called a Fermi Dirac distribution, okay, which is given by f of E is 1 over exponential of E minus EF over kBT plus 1, right. So in dilute gas you have Boltzmann distribution that describes the number of atoms in an excited state, right. Whereas, if you are looking at semiconductors, you essentially have to take into account this Fermi Dirac distribution. Just for completeness, I basically say this probability of occupying an energy EM is given by exponential of minus Em over kBt. Why are we talking about all this? Because as we move on to understanding absorption and emission, we will realize that some absorption and emission depends on the kind of atomic system that you are dealing with. Okay, it is different for these two atomic systems, right. And we will look at traditional atomic systems where you model this as a dilute gas of atoms, and you will follow Boltzmann distribution. And then you go on to looking at semiconductor light sources, right. And then you say in that case you will have to follow Fermi Dirac distribution. So, you need to understand what is the kind of material that you are dealing with, how can you characterize that material, okay. And lot of the emission characteristics depend on these aspects. But luckily we just do these two classification and we are done with it, right. So, it is either this or that, and of course we will see examples of this system versus that system, how the emission process is, emission and absorption process as well. Yes. For example, I mean just thinking about the absorption process, you can say that absorption in this can correspond to multiple specific frequencies, or maybe there are bands of frequencies, because these things are typically split around their center. So, you have bands of frequencies, but you have only specific bands of frequencies where you have absorption. Whereas here, if your frequency of the photon is such that the energy of that photon is less than the band gap energy, what happens? If it is less than the band gap energy, it just goes straight through. There is no probability of absorption because there is no higher energy level that it can go to, it is forbidden, right. So, you need energy, at least that band gap energy, before you can actually have that absorption happening. But once you achieve that, you will see that all these energy levels are relatively closely packed, then it is almost like a continuum of absorption that is happening, right. Beyond a particular frequency, right, absorption will be almost continuous, whereas here it is only in specific bands that you have this absorption happening. So, this is actually very nice from a spectroscopy perspective, because you can turn this around and say I can detect specific gases, let us say, right. I can detect specific gases based on where they absorb, right. So, each, you say carbon dioxide, you say oxygen, nitrogen, whatever, right, each one of them have a very specific energy level structure. So, they absorbed only at specific frequencies. So, when you are looking at their absorption, that is like a fingerprint, okay. If you see this fingerprint, then that corresponds to one element. If you see this fingerprint, that corresponds to another element, and so on, right. Based on the, you can do absorption spectroscopy and identify different gas species or different species in general, chemical species in general, because each one of them have their own unique fingerprint corresponding to these specific absorption that is happening between energy levels. Whereas here it is, yes, you can say that okay, I am doing the absorption spectroscopy and only beyond a certain frequency it starts absorbing. So, then you say okay, I can figure out my band gap energy based on that, but beyond that you cannot tell what exactly that material is. Okay, I wanted to go to one more concept, or maybe I will just give you a hint about this and we will continue this in the next lecture, right. So, I am looking at this expression and I am starting to read into it from perspective of what is the relative value of kBt and h nu, because based on those relative values, the value of the probability density of emission changes quite rapidly. And if that changes, if you go back and look at this, that actually where that comes into the picture is determining which is more probable, spontaneous emission or stimulated emission. Okay. So, if rho em the probability density of emission is high, then you can say stimulated emission would be the dominant mechanism, which is what you may want when you are amplifying something, right, or when you are building a laser, right. On the other hand, if that quantity, that probability density is very small, if it is a small number, then spontaneous emission is the dominant mechanism, which is why we have this light emitting diodes and all other, it is primarily spontaneously emitted sources. Okay. So, we want to look at different possibilities. So, specifically one observation would be that kBt is greater than delta E. It's greater than the energy difference between these two energy levels that we are considering. So, what do we have in this case? In this case, there is actually equal probability maybe that an atom can exist or an electron can be in this energy level or that energy level. Okay. So, the energy levels themselves they broaden and overlap, and in this case what we will see is the spontaneous emission rate or in general rho em the emission probability density is very low, and the spontaneous emission rate is far greater than the stimulated emission rate, which is what we have for thermal light sources. What is an example of a thermal light source? This tungsten filament lamp, right, the incandescent lamp. So you have this, and then you come up with this other observation that to have stimulated emission, one of the necessary conditions is that your delta E is far greater than kBt. Okay, but then you still need a fairly large value of rho em. So in which case you will find that you need to somehow get atoms to go to a higher energy level and maintain atoms at a higher energy level with respect to the lower energy level. Only when you have that inversion of population, that is when you will get stimulated emission. Okay. We will look at all those conditions in the next lecture. Okay. Thank you.